Hello, ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be talking about the second portion of Chapter 7 in Zumdahl, the 7th edition. It is titled Atomic Structure and Periodicity. So the last time that we spoke in Part 1, we were talking about the Bohr model of the atom. And in case you don't remember, the Bohr model of the atom has kind of a nucleus in the middle, and then you have a little kind of, we're going to call it an orbit, where you can find an electron, and each orbit is basically like a concentric circle, right? So you've got like a level 1, a level 2, a level 3, 4, etc. And so for the hydrogen atom, this gave us an explanation for emission spectra, which are these little lines that we see on this little pictogram or picture, right? So it was great for hydrogen. Very easy to calculate. We could utilize a simple equation to figure out and predict what colors we would see in an emission spectra. But the only problem was that Bohr's model broke down after hydrogen. If you try to apply this to helium or lithium or beryllium, it just doesn't work. So what we really need to get at is what's going on. If the Bohr model of the atom works for hydrogen but nothing else, then it's probably not the best model of the atom. So the first thing we need to talk about is that one of the main reasons why Bohr's model breaks down is because we have these orbits, like you can see here, for where electrons can be found, right? But in reality, we can't really know a detailed pathway that an electron is taking in an atom. So in other words, it looks totally, reasonable that you'd have an electron that's zipping around in a circle like this. And that's what most people picture when they picture an atom anyway, is electrons going in a little circle. But in reality, that's not the case. So that's one of the reasons why we have a different model of the atom that we use now instead of just the Bohr model of the atom, which everybody's kind of used to. And so this is kind of exemplified in the Heisenberg uncertainty principle, which says that if you know the position where an electron is located, you can't know the momentum of that electron. If you know the momentum of an electron in an atom, you can't know where it is positioned. And so this kind of paradox is described in this equation, which you really don't have to worry about. But I decided for completion's sake to include it. But what we have here is delta x, which is the uncertainty in the particle's position. We have delta mv, which is the uncertainty in the particle's momentum. And then you have this, little symbol here, greater than or equal to h being Planck's constant divided by 4 pi. So this is kind of a mathematical representation of the Heisenberg uncertainty principle. And it's one of the main reasons why, like we just said, the Bohr model of the atom isn't exactly very precise. So then what exactly do atoms really look like? Well, the first thing that you need to recognize is that the nucleus is still in the middle and contains protons and neutrons. That part was never really up for discussion, let's say. It's really just the electrons, right? So the electrons are the tricky ones. Another thing that is still true is that the atom is mostly empty. There's not a lot there. You have a nucleus in the middle, a lot of empty space, and then an electron, or 2 electrons, or even 1,000 electrons, okay? But the atom is still mostly empty. If you were to, randomly select a little section of an atom, you'd probably end up with nothing. That's kind of the point. Now, what about the electrons themselves? So this is where we start to differentiate ourselves from the Bohr model of the atom. So the electrons have interesting wave particle properties and are distributed in what we call orbitals. And you might think, oh, okay, those little circle things. Those aren't really orbitals. Those normally are considered orbits. I know that sounds very semantic, but orbitals are different. So what are orbitals then? In the quantum mechanical model of the atom, an orbital is the likely location where you will find an electron, like in the 90 to 95% chance mark here, which, if you know statistics, this is very, very important. But the whole point is that it's a location where you are likely to find an electron. You can't know with 100% certainty it's there, but 90 to 95% is pretty certain that makes sense from a probability standpoint. And so you can really think of orbitals as probability distributions. And so I'll show you a picture of what that looks like in a second. But the idea of a probability distribution is it's kind of like a map. Let's call it like like a little map. Each dot representing a possible location for where you could find an electron. And the more intense the color on the map, the higher the probability is where you would find your electron. So for the simplest wave function, right, this is what that looks like. So let's pretend like the very center of the atom, that's the nucleus. Notice it is darker here, and it gets lighter and lighter and lighter as you go out. So what this is really showing is the fact that it is highly likely that you find the electron pretty close to the nucleus. And as you get further and further away from the nucleus, it becomes less and less likely for you to find your electron. Now remember, an orbital is just the 90 to 95% probability distribution area, right? So is there a chance that you find your electron over here? Yeah, it's unlikely, but it's possible. And so you can see that what you kind of have when we look at a graph of it is the further away from the nucleus you get, the more unlikely it is to find your electron. And then also notice that the closer you get to the nucleus, the more likely you are to, get your electron or find your electron, but it never quite hits this zero. And that's because you will never find your electron inside of the nucleus. That's not how that works. Okay. And so you can think of it, if we superimpose Bohr's little orbits here, that you kind of have this distribution where you have this distance from the nucleus where there is a peak, let's say, for where you would be able to find your electron, and then it kind of goes away into nothingness, into 0% probability as you get infinitely far away from your atom. So relative orbital size. So how big are these orbitals? They're very difficult to define precisely, and instead you can think of it as a wave function, but we can picture them like a three-dimensional electron density map. Okay, and so what you get is every dot representing a possible location where that single electron might be. So we're still only looking at a single electron. Picture this, right? We have an atom. I take a picture, and then, okay, the electron was here. And then I take another picture, the electron's here. Take another picture, it's here, 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 here. If you superimpose them all on each other, you can start to find patterns, right? It is very likely for me to find my electron here, less likely to find it further out. And that's kind of what orbitals are. They're defined mathematically, but you can experimentally see, if that makes sense, quote unquote, them by taking a snapshot and then graphing that information in 3 dimensions. And so again, this is a 1s orbital, which is the simplest type of orbital we're going to ever be discussing. And the radius of your atom is defined as the area that you can find where you have a 90 to 95% probability of finding your electron. So otherwise, how would we describe the shape if there is a 5% chance maybe that I find an electron all the way over here off the screen? Instead, we say, okay, we're just going to close in where you have a 90 to 95% chance of finding an electron. And so that's where we get these different shapes from. Okay. And like it says here, orbitals do come in different shapes and different sizes. So here is an example of some s orbitals. And don't worry too much about what this means. We're going to talk about it in a bit. But this is like the simplest one. Okay. And so notice it is just basically a sphere. That's it. And then notice that this is, a little bit more complicated. Okay, it's the next level up. And notice that they have what we call here a node. A node is a region where you can not find your electron, which is very interesting. So again, if we were mapping this, you have a 0% chance of finding it for this particular shape right against the nucleus. You also have a 0% chance of finding it basically infinitely far away from the nucleus. But here, there is literally a 0% chance that you find it in this little ring. So there's no way for your electron to exist in that little ring. But it can exist here or here. So it can exist in this little middle area or in this outer area. And so they get more complicated as we go on. And so again, this one has a couple of nodes. And just realize that if you were to, take a slice of it, which is what we're seeing here, this is what it would look like. If you're looking at it, though, three-dimensionally from a probability distribution kind of point, and you're just looking at it as an outside observer, you would just see a sphere. And the sphere would just be getting a little bigger and bigger and bigger. P orbitals look crazy. Here's an electron density map, right? Where, again, they've been basically taking a snapshot of where the electron that they've been looking for is. And so you get these cool little dumbbell shapes, again, going diagonally, going horizontally, and going vertically. We call those, by the way, I guess I should have said p orbitals. D orbitals look even crazier. You have these four-leaf clover-like shapes, which again are pointing in different directions. My favorite one is called the DZ squared, or the DZ2 orbital. It has a cool little donut going around the middle of it. But notice that they're very similar shapes. You have these asymptotes, basically these nodes where you can't find electrons, but you have these areas where you can very obviously find electrons. And then F orbitals are absolutely insane. They come in all of these different shapes. You've got all of these different nodes all over the place. But again, those are the four shapes, quote unquote, of orbitals. Now let's talk a little bit about ground states versus excited states for electrons. So the most stable arrangement of electrons in their orbitals, we call that the ground state electron configuration. And that's important because the ground state is where your electrons reside in their lowest energy levels. So in other words, it is where you would find electrons for any atom from the periodic table if you didn't apply any energy to it at all. It's just, where would you find your electrons? The ground state describes where you would find your electrons. Now, keep in mind that if you are now giving your atom some energy, those electrons can go into a higher energy state, and then we call that an excited state. And it actually connects very well with something that we already discussed before when we were looking at Bohr's model of the atom. And that is that when you have electrons that are in a higher energy state, an excited state, what happens is the electron will move from one orbital to another orbital. Now, Bohr's model are these, little circle things. Now we know that, we have all these other shapes of orbitals, and there are locations where electrons can't actually be. There are these nodes and stuff, right? But if you have an electron going from a ground state energy level to a higher energy level, what's going to happen? Well, it's going to absorb some of that energy, and then eventually it's going to go from an excited state back to a ground state, and it's going to give off a wavelength of light. And that wavelength of light that it gives off, we call, again, just like Bohr found for hydrogen, an emission spectra. And we can calculate it using E equals hv, h being Planck's constant, v being the frequency. Okay? So it does connect. The quantum mechanic model and Bohr's model do connect. Okay, now let's talk about orbitals themselves. So orbitals are represented by a number and a letter. The number tells you the approximate distance from the nucleus that electron is, and it ranges from 1 being the closest to the nucleus to 7 being the furthest away from the nucleus. The letter tells you the shape of that electron density map. And so remember, I told you didn't have to worry about it at the time, but that was only a couple minutes ago. So what are our shapes? They are S, P, D, or F. And in case you're wondering, does S, P, D, and F mean something? Yes, it does. But in reality, they don't really mean anything anymore, okay? So they used to actually point out particular features that you might find on emission spectra and absorption spectra and stuff, but that isn't really true anymore. So we just use the letter S, P, D, or F to describe them. So again, but you need a number and you need a letter. So all of these random examples, 3D, 1S, 5D, 4S, 7D. These are all examples of orbitals, okay? Different orbitals that exist. Again, the number is pointing out what the distance is from the nucleus, and the letter is telling us the approximate shape that we might find for our electron density map. So what is the pattern? Here is a pattern. And notice that, some of these, they're only single, I guess I shouldn't say single. They're only particular orbitals that are possible. So for example, at the 1 energy level, meaning the closest to the nucleus you can get, you have the 1s, okay? at the second energy level, so you're now a little further away from the nucleus, we have the 2s and the 2p. At the third energy level, so now we're even further away, we have 3s, 3p, 3d, etc., right? So notice that there's no such thing as a 1p or a 1d or a 1f. As we kind of go up, further away from the nucleus, we kind of gain an extra shape that is possible. And we cap out at the F's, though, because there are only 4 different shapes, okay? Now, you might think, okay, this doesn't seem too hard. It's 1s, and then you have 2s and 2p, and you might think that it's all sequential. Now, here's where it gets a little more difficult. They're not sequential. So, yes, in case you are wondering, 1s is where we start putting electrons at the closest we can possibly get to the nucleus. But once you get beyond a particular point, it gets a little bit more difficult to describe what's the next energy level. And so I'm going to show you what they are. But generally speaking, lower energy levels are, over here by the 1, and higher energy levels are over here by the 7. Okay, but here's the order. Okay, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p. So at first it looks okay, not too bad. And then right here is where it starts to get weird. You go 4s, then you go to 3d, then you go 4p. So what's the deal with this? Well, there's a very particular reason why these arrows exist in this diagram, okay? And so here is the shortcut way of remembering the order from lowest energy to highest energy orbitals that exist in an atom, okay? So you follow the arrow. So I have 1s, great. 2s, great. 2p, 3s, great. 3p, 4s, great. 3d, 4p, 5s. And you basically follow the arrows as you go through all the way until you get to 7f, okay? And so these little arrows are kind of the way that you remember, okay, what order am I supposed to put these in from lowest energy to highest energy, okay? I know that sounded probably a little bit complicated, but this diagram is a fantastic summary of that. Now, let me explain to you why it's important to know lower energy to higher energy orbitals. And there's a reason for that. So more on that in a little bit. Little side note, s orbitals. So anytime you see an s orbitals can only hold 2 electrons. Okay, p orbitals can hold a maximum of 6 electrons. D orbitals can hold 10. F orbitals can hold 14. Now, this seems fairly arbitrary. 2, 6, 10, 14, like what's going on with that? And I'll show you in the pictures that I had already shared of orbitals why that is the case. Okay, why? Here's the first one, s orbital. So here's an s orbital. You can fit 2 electrons maximum in here. So again, remember, electron density is telling us that the darker it is, the more likely you are to find an electron. And so that's true if there are 2 electrons. You're more likely to find both of your electrons here, but you could find maybe one here and one here, or you could find both over here, but that would be unlikely, okay? Or more unlikely, let's say, than finding them closer. So 2 electrons here. Remember, these 3 things for the p orbitals, guess what? You can fit 2 here, 2 here, 2 here for a maximum of 6. You probably know where this is going now. For d orbitals, remember we had these 5 shapes. You could fit 2 here, or 2 here, or here, or here, or here. That means you have up to 10 possible locations for electrons. And last but not least, we had 7 different shapes for f orbitals. So of course we can have 14 electrons if each of these can hold 2. Now, what can we infer about this pattern from the periodic table? Okay, so let me tell you that the periodic table is not just useful because it contains all of the elements from, the universe. It's important because everything that I just talked about can be found if you know where to look on the periodic table. Now, remember, the number part of the orbital tells you how far something is from the nucleus. Guess how many rows we have on the periodic table. 1, 2, 3, 4, 5, 6, 7. That is not a coincidence. This is what we would call, generally speaking, the 1s level. This is, generally speaking, the 2s level, okay? 3s, 4s, 5s, etc., okay? Now, you might also think the periodic table looks weird. Look at all these weird little bits that are sticking out and stuff. Why is that the case? Well, here's the reason why. Take a look. I have 2 columns here. How many columns here do I have? 6. How many columns here do I have in the middle? 10. How many columns here do I have in the lanthanide and actinides that are always separated from the periodic table? 14. What do those numbers resemble? Well, remember, in s orbitals, I can fit 2 electrons. In p orbitals, I can fit 6 electrons. In d orbitals, I can fit 10 electrons. In f orbitals, I can fit 14 electrons. So not only is the periodic table organized by the number of protons, it's also organized by the number of electrons. And the shape that we get is actually related to the electrons in the orbitals for those particular elements. So we call the first 2 columns here plus helium, okay, because helium kind of gets separated, but you can very much imagine that this is actually right here. We call that the S block. We call these 6 columns here the P block, these 10 columns here the D block, and the final 14 that are all separated the F block. Okay? And notice that the distance you are from the nucleus is getting further and further as you go down the periodic table. All right, let's talk about orbital diagrams. In an orbital diagram, boxes are used to represent the locations of electrons. Arrows are used to represent the electrons themselves, okay? Now, each box can only hold 2 electrons, and boxes are labeled from lowest energy level to highest energy level. So why is it important to remember that weird little pattern with the little diagonal arrows? It's because whenever we are diagramming orbitals, we need to remember that we have to go in order from lowest to highest. 1s, 2s, 2p, 3s, 3p, 4s, 3d, etc. Now, what about s orbitals? So s orbitals have 1 box, p orbitals would have to have 3 boxes, d orbitals would have to have 5 boxes, because remember, each box can only hold 2 electrons. So since each box can only hold 2 electrons, if you want to have up to 6 electrons in a p orbital, right, that means that you would need to have enough boxes for that to work. Okay, now let's actually talk about the rules here. So the Aufbau principle. The Aufbau principle, and Aufbau is just a German word. I think it means filling, like to put things in order. So the Aufbau principle says that electrons, in our case arrows, are always added from lowest energy to highest energy. So the way I always think about it, our electrons are lazy. They will not want to expend energy if they don't have to. So they will always exist in the lowest energy state. And then, you give them some energy, sure, they'll move up, but they always go from lowest to highest by default. So for example, if we have these boxes with these arrows in them, 1s, 2s, 2p, 3s, 3p, and notice that, these p orbitals, these 3 boxes represent the 2p orbital level, because once again, remember, we can fit up to 6. So if we can fit up to 6, these 3 boxes must represent the p orbital level. We can't skip boxes. So in other words, this is totally and completely incorrect if you're trying to follow the Aufbau principle, because you have to start adding arrows to the lowest energy level before you can move up to a higher energy level, okay? Hund's rule. Hund's rule says electrons, so in our case arrows, must be added to separate orbitals of equal energy before moving on to higher energy orbitals. So the way I think of it is electrons like to take up their own space, okay? They don't want to be forced to pair up if they don't have to. And so I always think about it like if you're on a bus. So here is the way that you would fill in electrons if you're following Hund's rule. Okay, so think about this. I have 1 box for the 1s, okay? So if I have 1 electron, I'd put 1 arrow in it. If I have 2 electrons, I have to pair them up. There's nothing I can do about it because remember, off-ball principle said I have to go from lowest energy to higher energy. So I can't just skip a box because I want to. Okay, same thing with 2s. Okay, if I have 3 electrons, I would put one more electron in this box. If I have 4 electrons, now I have to pair them up. Now, where this becomes important is when I have multiple boxes representing an energy level like the 2p. So I always say, think about it like being on the bus. Let's say that you have 3 empty rows of seats and you are the only person on the bus. Of course, you're going to sit probably wherever you'd like, but let's say we sit right here in the front. What if I now add a second person to the bus? If you don't know anybody, right, you're just the second person to get on, you're probably not going to want to sit next to this person you don't know, so you spread out. This is allowed because these have the same energy. Each box represents the same energy level. All of these boxes are the 2p. Okay? Third person that doesn't know the other two. They're going to probably go to the third row. Okay, now what if a fourth person joins? We still have 3 empty seats, but now they're going to be forced to pair up. And then what if we add a fifth? And then what if we add a sixth? Hund's rule basically says that before you move on to another energy level, you want your electrons to spread out, and that will minimize, in our mind, repulsion. Remember, electrons are negatively charged. If you're putting a negatively charged thing next to another negatively charged thing, they're going to repel each other. But if they have no choice, of course they'll pair up. Like in the 1s, there's no choice. S orbitals can hold 2 electrons. You can't move on to the next energy level until you've filled in all of your space. But if you have the p orbital here, you have 3 boxes. So you can spread yourself out before you pair up. If you had a d orbital, you'd have 5 boxes. Again, same thing. You'd spread yourself out to all 5 boxes individually before you would pair up. Now, Pauli exclusion principle, I always save this one for the end because it signifies something, but it's not that important. So notice that in all the examples that I've done, I have not put 2 up arrows or 2 down arrows in a box. So the Pauli exclusion principle basically says electrons, so arrows, must have opposite spins if they are in the same orbit. Now, up arrows and down arrows represent different spins. You can think about it like, an electron that's spinning clockwise and an electron that's spinning counterclockwise. You can't have 2, clockwise spinning electrons in the same orbital. So the Pauli exclusion principle basically just states that you can't have 2 up arrows or 2 down arrows in a box. And so this is the reason why. It's the Pauli exclusion principle. So now let's take a look at this. Which of these orbital diagrams is correct? Okay, so 3 of them have mistakes, and 1 of them is totally acceptable. Can you point out which one, A, B, C, or D, is the correct one? Can you pick it out? And the answer is, dun, 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 letter D. Letter D is the only one of these that is correct. And what rule is being broken for the other 3? So let's take a look at this first one. I have 2 arrows. I have 1 arrow. Then they skip to the next box. Is that allowed? Definitely not. This is an off-ball principle violation. What about this one? Okay, up arrow, down arrow, up arrow, red flag, right? This is a Pauli exclusion principle problem. Okay, what about this one? Up arrow, down arrow, up arrow, down arrow, up arrow, down arrow. Remember, Hund's rule says that you have to spread out the electrons individually, like here or here or here, before you start pairing them up. So letter C is a Hund's rule problem. Now let's draw some ground state orbital diagrams for various elements. Let's start with carbon. So find carbon on your periodic table, and let's see if you can draw an orbital diagram for it. Okay, I'll show you. It would look something like this. So notice I have 2, 4, 5, 6 arrows. Why 6 arrows? Because carbon is the 6th element on the periodic table. Whatever the atomic number says, that is the number of electrons you have in your diagram. All right, let's try the next one. Try drawing chlorines. Correct answer. Go all the way up to the 3p for this one, right? So why? If you count, I have 17 arrows in my picture here because chlorine is number 17 on the periodic table. Notice the boxes are spread out, 1s, 2s. We have 3 boxes representing the 2p, 3s, 3p, and I could continue. So I could do the 4s next, and then I could do the 3d. So you can keep extending this outwards. And in fact, we're going to do that in this next one. We're going to draw the ground state electron configuration, orbital diagram for iron. So see if you can find iron on the periodic table, figure out how many electrons it has, and draw the proper arrows in the proper boxes. Correct answer. Notice that I went all the way up to the 3D. Why? Well, iron is number 26. And so again, if I'm following my pattern, it goes 1s, 2s, 2p, 3s, 3p, 4s, 3d. This is where the exception, this is where that diagram that I showed you starts to become extremely important because you go from 4s to 3d. And then after that, you go back to the 4. So then we go to the 4p. So it becomes very important to remember what order all of these go in. But notice that we spread out all of our arrows before we started pairing them up, just like we did before. All right. Last but certainly not least for this lesson, we have electron configurations. So electron configurations are a numerical way of showing the arrangement of electrons in an atom using superscripts. So if an orbital diagram is a visual representation, an electron configuration is like a shortcut version of that. And that's kind of the way I like to think of them. It's like a short, concise way of representing an orbital diagram without having to draw boxes and without having to draw a bunch of arrows. So the superscripts are used to represent the total number of electrons in each orbital. So notice for orbital diagrams, we had like 3 boxes to represent the p orbital, okay? We don't need to do that for electron configurations. We can just basically count how many arrows there were. Oh, great, there were 6 arrows in that. That means that we would put a 6 as a superscript. So here's a good example. Neon has 10 electrons. And the way that we would write this would be 1s squared. And so the way you say that, though, is 1s2. 2s squared, that's 2s2. 2p, and then you wouldn't say to the 6. The way we actually would say it would be 2p6. So the way I would write the electron configuration for neon would be 1s2, 2s2, 2p6. And so again, notice neon is number 10 on the periodic table here. And if we add up the superscripts, 2 plus 2 plus 6 is 10. If I were to draw the orbital diagram for this, right, I would have a box with 2 arrows, a box with 2 arrows, and then I would have 3 boxes representing the 2p, but they would be full with 6 arrows total. So again, it's kind of like a nice shortcut way of doing that. And so here are some electron configurations. Can you use your periodic table to determine what the actual identity is of these elements in their ground state? All right, so let's take a look at this first one. That would be sodium. Again, 2, 2, 6, 1, that's 11. So number 11 on the periodic table is sodium. Here we go. Okay, add all those together. You get manganese's atomic number. Add these together, 2, 2, and 2. That should be pretty easy, right? That's just carbon. That's 6, 2, 4, 6. Here I have 2, 2, 6, 2, 4. Okay, that would be sulfur then, if I'm looking at my periodic table. All right, so last but not least, the abbreviated electron configuration. So electron configurations can get out of hand very quickly because you have to literally list each orbital, and only the valence electrons are really of any interest to chemists. The core electrons, they don't really do anything. So there is a shortcut way. So I'm teaching you another shortcut. So if orbital diagrams are like the hard one, electron configurations are like a shortcut. Abbreviated electron configurations are like a shortcut to a shortcut, okay? And so here's kind of how that works for us, okay? The way that we do this and fix it is you basically say, okay, I'm going to pretend like the noble gas on the periodic table, the previous noble gas that appears, contains all of the core electrons that I need to represent my electron configuration for this particular element, and you put that in brackets. So for example, you would put, like, if you wanted to represent 10 core electrons, neon's number 10, right? So you would just put it in brackets like that. And then you can continue naming your orbitals from that point onwards. So for example, right? You could say, okay, I'm going to put, I don't want to have to list 1s2, 2s2, 2p6. All that stuff gets really boring. So for strontium, I look at my periodic table, I find strontium. What's the previous noble gas before strontium? It is krypton. So krypton represents the core electrons of strontium. And then I just say, okay, the only electrons that I really care about are the 5s2 electrons. So the 2 electrons that are in the 5s level. And so you just continue writing it like normal. Phosphorus, same exact thing. What's the previous noble gas before it? It is neon. That contains 10 electrons. Great. So then 3s2, 3p4, that would complete my electron configuration. And the nice thing is you can just kind of add them up still. So neon is 10, has 10 electrons. This has 2 and 4, so 12 plus 4 is 16. And guess what? Phosphorus is number 16. Okay, so it's still the same thing. Let's see if you can determine the expected abbreviated electron configurations for the following 3. So we have sulfur, barium, and europium. Okay, so for sulfur, let's see if you can get that right. There we go. So we got Ne, 3s2, 3p4. Right, next up, barium, we have xenon, and then we have 6s2. Europium, we have xenon, we have 6s2, 4f7. Again, remember, you just pick the previous noble gas that appears before your element, and then you just continue writing your electrons as determined by our Aufbau principle from lowest to highest, and then how many electrons can you fit in each of those levels. And then last but certainly not least, what happens to the electron configurations when we talk about cations and anions? So recall that cations are positively charged particles. So we're talking about an atom that has lost some electrons. And then anions are negatively charged ions, right? So they are ones that have gained electrons. So the interesting thing about cations and anions when you write out their electron configurations is that they always will share their electron configurations with the ground state electron configuration of a noble gas. So just to connect everything to what we've already seen and what we've already learned, if you were to take the electron configuration of the sodium atom, right, which has 11 electrons, so if we count each of these, this would add up to 11 electrons, right? What you would write for the electron configuration would be this: 1s2, 2s2, 2p6, 3s1. That's the complete electron configuration, right? When it loses its single electron, the reason why it loses a single electron is because it has this. It has in the 3s energy level a single electron that's unpaired all by itself. So it would pretty readily get rid of that electron because it's all by itself in another energy level that's pretty far away from the effective nuclear charge of the, of the nucleus. So when it does that, it basically eradicates this, and now we have 10 electrons. So you'd write an electron configuration of 1s2, 2s2, 2p6. Now, what electron configuration is this? It's the electron configuration of neon. So it's important that when you're looking through and writing ground state electron configurations for things, that you know whether you're talking about an atom, like this, or if it's an ion. Because if it's an ion, there are plenty of ions that exist that have an electron configuration that would be the same as neon, or the same as argon, or the same as helium, or the same, so the whole purpose of me telling you this is just so that you recognize that if you see an electron configuration for an ion, like sodium here, that lets you know that, okay, great, I have lost an electron. That's why I have this electron configuration, which looks like it's neon. So unless they give you a piece of information otherwise, always assume that they're talking about atoms. If they're talking about ions, though, then recognize the fact that you're going to have to either gain or lose electrons, and that's going to give you an electron configuration that resembles another noble gas. All right, so that takes us to the end. That's the end of this section. There is technically another section that goes on to the periodic table. I'm going to have to make that part 3. I didn't want to make this over an hour long. But thank you very much. Please make sure you like this video. You can subscribe to my channel. Part 3 will be coming out shortly, since it's just going to be about the periodic table. It shouldn't take long to actually make. But yeah, so stick around, and if you have any questions, please leave a comment. Thank you very much.